All right. Hello, everybody. I know the lighting is really bad today. I had to turn my desk around because I had to pull out our day bed. So we have the real bad backlighting. It is what it is. We're just going to handle it. It's only one video. All right. So today we are starting Unit 8, which is sequences and series, which should be a little bit familiar for some of you. For pretty much all of you, actually. You should have all seen this in Algebra 1 and Algebra 2. But the first day might be a little bit strange. We've talked about limits before, but today we're going to look at limits a little bit differently. We're going to kind of re-talk about them because it's been a long time since we've talked about limits and what they are and things like that. Um, so that's kind of what we're looking at today. It's kind of like our intro day, and we're going to go over some important vocab words that are going to come up in this unit, obviously, because we're talking about it, but mostly next year in calculus. You actually do a lot with limits and you do a good amount of work with sequences and series. So here we go. Okay, so first let's talk about what a sequence is. I think that's kind of a good place to start. Sorry, I like moving all these screens around. All right, so a sequence is just an ordered progression of numbers, right? And these numbers generally have some kind of pattern to them. So when you have a sequence, generally, not always, because there are sequences that don't have a distinctive pattern, but for this class anyways, we're going to be looking at these ordered kind of progression of numbers with some type of pattern. All right, so that's our sequence. So come on, an ordered progression of numbers. All right, so for instance, right, example 2, 4, 6, 8, dot, dot, dot. That is a sequence, right? So it's an ordered, right? There's a specific order, progression of numbers, right? Progression just means like we are increasing or decreasing at some rate. Okay, so there are two types of sequences. There's what we call a finite sequence, which is a sequence that has an ending, right? Finite means we have a start, we have a distinctive ending point. All right, so finite sequences, these ones are nice because we know what all the numbers are, right, in a finite sequence. All right, so an ordered, oh no, a sequence, sorry, I was looking at the wrong thing. A sequence that has an ending term. All right, so unlike the one that I gave, like as the example in my sequence definition, how we have the dot, dot, dot at the end, you would have a final point. So it would look something like this. So example 2, 4, 6, 8. That's it. There's no dot, dot, dot. This progression does not keep going. 8 would be our final turn. So I would say that this is a finite sequence. All right, as you can probably guess. Hi, baby. She's on the floor hanging out with me. As you can probably guess, an infinite sequence is a sequence that does not have an ending term. It does continue on forever. All right, so infinite would be a sequence with no ending term. Ending term. All right, and like I said, this one is kind of like the example that I gave for sequence. You have the dot, dot, dot at the end. So 2, 4, 6, 8, dot, dot, dot. That indicates it will keep going. There are more numbers after 8, right? So this is an infinite sequence. All right, so finite has an end, infinite, no ending. That's the basic summary of kind of that section. All right, now we're going to get into limits. So just to recap, limits are like our end behavior, like what is our, generally when we were doing this with functions, right? So we would say, what is our function approaching as x goes to positive infinity or x goes to negative infinity, right? So our limits are kind of there. Another word for them is our end behavior, right? So what is our function doing as it goes off the screen? All right, and the notation for limits, you have the LIM, right? So limit as x goes to either positive or negative infinity, we'll just do positive infinity, of some function, equals, and then you say what it's going to. Could be a number, could be like 1, 2, -7, whatever, could be infinity. So sometimes we have functions that go forever, you know, either go up positively in as x gets bigger, the values go up, or they go to negative infinity or whatever. All right, so your limit is what is your function doing as it's going towards infinity. Now, when we did our rationals unit, we talked about limits towards asymptotes, which that's a different topic. This unit, we're going to be specifically looking at what we would call like an end behavior limit, because we want to know what are these sequences doing as they get larger and larger, specifically for these infinite sequences. Are they approaching a number? Are they getting really small and getting close to something, or are they just getting bigger without bound? All right, so that's what we're going to look at now. So the limits of sequences. All right, and like I said, this is the value or term that a sequence approaches as it goes on forever. And you might be looking at, you know, the infinite sequences, and you're saying 2, 4, 6, 8, 10, 12, 14, 16, whatever. That's just going to keep going. It's not approaching anything except infinity. Well, truthfully, infinity is something, right? But it's not actually going towards a number. Well, there are sequences, though, that do approach a specific number. If you have, like, for instance, 1 over n, right, where your sequence is, you know, the number that you're putting on the bottom is getting progressively larger every time. Those ones do eventually kind of approach a value. All right, so that's what we're going to be looking at. So limits of sequences, this is the value or term that a sequence approaches as it goes to infinity. All right, so the value that a sequence, just shortening it to SEQ because sequence gets kind of long to write out all the time, approaches as it goes to infinity. I think that fits on the screen. No, infinity does not fit. To infinity. There you go. There we go. I got squished out. Okay. All right. And so then there are, based on these limits, there are 2 types of sequences. There are sequences that do what we call converge, and then there are sequences that do what we call diverge. All right, so a sequence that converges is a sequence that does approach some value. All right, not just infinity. All right. So converging means that our sequence approaches some unique value. All right, so let's converge. All right, these are sequences that approach. Approach, 2 R's, I think. A unique value. The limit exists. It's a number. I don't know how else to say this, right? So it means that you have a limit, right? The limit exists, it approaches some number. So infinity does not count as a convergent sequence, right? So if something is going to infinity, it's not really approaching anything, it's just getting larger without bound, right? So when we say something converges, it's approaching a single number, like 1 or 2. all right, then that means that diverge, it approaches infinity, or sometimes the limit just doesn't even exist. You can't even say infinity. You would say something like just limit does not exist. And that would happen with something that is that oscillates, so it bounces between two values. So for instance, our trig functions, right, when we graph sine or cosine, they bounce between 1 and -1. Those don't have limits, and we can't even say that they approach infinity because they don't. They go towards 1, or sorry, they go towards -1, then they go back to 1, then -1, then back to 1. So that one we would just strictly say like limit does not exist. It wouldn't even be accurate to say infinity. But anyways, diverge means the sequence does not approach some unique value. All right, it's neither, it will either go to infinity or negative infinity, or like I said, it could do what's called oscillating, where it doesn't even approach anything. It just bounces back and forth between two numbers. All right, so this is a sequence that doesn't approach a unique value. So we'll just do like examples. It goes to positive infinity, negative infinity, or oscillates. Bounce between multiple values. All right, and for these ones we would say the limit does not exist, right? So for converge, the limit exists. Diverge, the limit does not exist. All right, so the limit does not exist. And a shorthand way of writing this is DNE, does not exist. All right, so if you see that, that's a common term used in calculus. You will see DNE quite often. It stands for does not exist. All right, so that's like a little bit of math shorthand. Oh, I didn't even notice that my picture was in the middle of the, nope. I meant to move this part up here. There we go. All right, so DNE does not exist. All right, a little bit of Mean Girls reference in there. If you've seen Mean Girls, right, you know, the limit does not exist. That's this. Okay. All right, so next thing we're gonna look at is, okay, Miss Lastly, so we've learned about converging and diverging. How do we know if a sequence that doesn't have a graph, right? Because a lot of us use our graphs to figure out what the end value or end behavior is going to be. Well, sequences don't have graphs, they're not functions. So how on earth are we gonna figure out what the limit of a set of numbers is going to be? And it's actually something I already taught you. Bobo Boden eats DC. Yeah, we're using it again. All right, if you don't remember Bobo, we did this back when we were looking at rational functions and trying to figure out what the horizontal asymptote was going to be. And we used Bobo Botten to, like I said, figure out what horizontal is. Horizontal sideways. What our horizontal value that we were approaching was going to be. We're going to use the same technique for our sequences, and it actually works. So when you're doing limits of all sorts, Bobo Boden eats DC actually works for all of these limits. So a quick recap. Bobo stands for, so we're looking at our exponents, we're looking at growth, right? Is it, so usually exponents are a good way of figuring out if something's growing faster somewhere. So when we're talking about, you know, we're going to say Bobo is bigger on bottom 0. When we're talking about things that are bigger, we're looking at our exponents of our variables. All right. So remember, this is looking at the exponents of the variables. All right, so like I said, Bobo is bigger on bottom 0. All right, so if the biggest exponent's on the bottom, your limit is 0. All right, Botten, bigger on top none. All right, so equals 0, and we would say this one equals none. All right, so for this one, you would say DNE. The limit does not exist. All right, so if it's growing faster on the top of our fraction, all right, then there isn't a limit. It doesn't exist. All right, last but not least is eats DC. So exponents are the same, divide coefficients. All right, somebody didn't want to hang out by themselves on the floor anymore. So she's making her video debut. All right. So exponents are the same, divide coefficients. Okay, so that one, all right, so when you have it growing the same speed on the top and on the bottom, that is going to kind of, if something's growing equally, then what you end up with is just the coefficients, which is the number in front of your variables. That's going to be your limit. So how you're going to see all of them written. So for Bobo, you would say, so the limit as x goes to infinity of a sub n. So I didn't say this before, I probably should have. A sub n is your symbol for your sequence. So let's actually kind of backtrack a little bit. Oops, go up here. All right, so sequences, a sub n equals, and then you put your sequence right here. So a sub n is like your symbol for a sequence, where n is your term number. So like for the first term of a sequence, we would call that a sub 1. For the second term of a sequence, we would say a subscript 2. All right, so a sub n is the sequence itself, and then where n is our term number. All right, so I probably should have mentioned that, I forgot, but that's okay, I got it anyways. All right, so for Bobo, we would have limit as x goes to infinity of a sub n, so of a sequence, equals 0. All right, so we'll just highlight. That way that we know they match up. All right, for Botan, the limit of a sub n as x goes to infinity will equal dne. Does not exist. Boop-a-doo, boop-a-doo. And then last but not least, eats dc. The limit of a sub n as x goes, n goes to infinity. These should all be n's because the term number goes to infinity. All right, equals the coefficients like divided by each other. So you divide your coefficients. Okay. So that is how we're going to find our limits. All right, so it's actually pretty easy, and it's a skill that we've basically already done. So here are our examples. All right, so it says list the first 3 terms of the sequences, determine whether the sequence diverges or converges. If they converge, state the limit. So here we go. Number 1. All right, so we want to find the first 3 terms. So a sub 1. So we're going to plug in a 1 for n. So we have 1 over 1 plus 1, which is 1/2. The second term, a sub 2. So we're going to plug in a 2 for n. So we have 2 over 2 plus 1. So that's 2/3. A sub 3. So we plug in a 3 for n. That's 3 over 3 plus 1, which equals 3 over 4. All right, and we could keep going, right? We could go, but it only says list the first 3 terms. But you can see what's happening. So 1/2, all right, 2/3, 3/4, right? Our next one would be what? 5/6, 7/8, 9/10. So our number is actually getting bigger, but it's never actually going to go over a certain value. All right, so let's look at the limit for this one. So limit as n goes to infinity of a sub n equals. All right, so let's do Bobo Botan. So let's look at our exponents. On the top, we have an exponent of 1, right? N to the first, so exponent of 1. On the bottom, our biggest exponent is also 1, right? We have n to the first on the bottom. All right, so that is an EATS DC problem. This is EATS DC. Exponents are the same. So what we need to do is divide the coefficients in front of those highest exponent variables. All right, so in front of n to the first, we have a 1. In front of the n to the first on the bottom, we have 1. So divide coefficients, 1 over 1 equals 1. And that makes sense, right? So we have 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6. We're never going to get bigger than 1 because the number on the top will always be like 1 less than, but it's getting closer and closer and closer and closer to 1. So we would say our sequence is going to converge, that's an R, converge to 1. All right, let's look at the second one. All right, so first we're going to list out our numbers. So A1 equals, so that's 1 plus 2 over 2 times 1 squared. So that's 3 halves. A sub 2, that's 2 plus 2 over 2 times 2 squared. That's 4 over 2 squared is 4 times 2 is 8. All right. A sub 3, we have 3 plus 2 over 2 times 3 squared. So 3 plus 2 is 5, 3 squared is 9, 2 times 9 is 18. All right, so our numbers started at 3 halves, and every time it's getting smaller. All right, well, let's look at our sequence. Let's look at our limit. So the limit as n goes to infinity of a sub n equals, all right, and so let's look at our exponents. We have to the first on the top and we have squared on the bottom. So this one has a bigger on bottom. This is a bobo. And what it tells us is that if the exponent is biggest on the bottom, the limit is 0. And it makes sense, right? Our numbers are getting smaller and smaller, and they're going to continue to get smaller, which is going to make our fraction get closer and closer to 0. So our limit of our sequence is 0. All right, and since we have a value, we would say that this converges to 0. All right, I bet you can probably, I know, baby. Yeah, you're real heavy. Oh, I got one more example, and then we can go hang out together. Whew, she's real heavy. All right. So last but not least, problem number 3, and I'm sure, like I was about to say, you can probably guess where this is going, but let's just do this. Okay, so we'll start with listing our terms. A1, so this is 1 squared over 2 times 1 plus 1. It's 1 over 3. A sub 2, so our second term of our sequence is 2 squared over 2 times 2 plus 1. So that's 4 over 5. A3, that's 3 squared over 2 times 3 plus 1. So that's 9 over 6 plus 1, 7. All right, so we were at 1/3. Now we've grown to 4/5. Then we grow to 9/7. And as you can probably guess, the number on the top is going to continue to grow larger because we're squaring it. Whereas on the bottom, we're just multiplying by 2. So that's not going to grow as fast. So these top numbers are going to grow faster than the bottom numbers. So we're actually going to just continue to grow larger, just getting closer and, bigger and bigger and bigger. The number we end up dividing by is going to get so insignificant. It's just going to, our number's just going to keep getting larger, which is an indication that we probably don't have a limit. But let's check our rules. So we look at our exponents. We have squared on top, and we have to the first on the bottom. This is a bottom situation. Bigger on top, none. All right, so we're growing faster in the top of our fraction, which means our number is just getting bigger. All right, it's not going to approach anything. So when we do our limit, the limit of a sub n as n goes to infinity equals nothing. It's just going to get larger. So we would say does not exist. This diverges. All right, so that is This section, we will look more at limits when we start looking at specific functions, but that's basically a nice little summary. All right, until the next time, bye.